Okay, so let's find the Laplace transform of the sine of alpha t. And if we apply the definition, we get the integral from 0 to infinity of e to the minus st times the function sine alpha t dt. And to perform this integration, I'm going to do an integration by parts. So on the side, I guess I'll write, I'm going to let u equal to, and I'll choose the trigonometric function. So I'll choose the sine of alpha t. And so if u is the sine of alpha t, then the derivative of u with respect to t is going to be the cosine of alpha t times the derivative of alpha t. So, and that's just going to give me the alpha. So I get du equals an alpha cosine alpha t dt. And since u is the sine of alpha t, I'll let dv pick up everything else to e to the minus st dt. And v is going to be the integral of e to the minus st dt. So I'll just get a minus 1 over s e to the minus st. So applying this integration by parts technique, where I've written my integrand as a product of a function and the derivative of another function. I now know that this is going to be u times v, so I'll get, let's say, a minus sine alpha t over s e to the minus st, evaluated from 0 to infinity, minus the integral of v du. So v is a minus 1 over s e to the minus st, and the du, I have alpha cosine alpha t. I guess I just throw the dt on the outside. So let's evaluate this first part, and let's see. So at the upper limit, I'll have the sine, I guess, oscillating, but this exponential, as t gets really large, decays to 0, minus this minus sine of 0 over s. The sine of 0, of course, is 0, and times 1 for e to the 0. But anyway, I'm just left with 0. So I have a minus and a minus. That becomes a plus. I can pull out an alpha over s since they're constant. Put my limits of integration. The integral from 0 to infinity. And so I have e to the minus st cosine alpha t dt. So again, I want to do another integration by parts, and I'm going to stick with the trigonometric function for u. So I'm going to let u equal to the cosine of alpha t, and then my du, so the derivative of cosine is the minus sine, so I'll get a minus alpha times the sine of alpha t dt. And since I chose that for u, then my dv is going to be the same as it is above, e to the minus st dt, where v is going to be a minus 1 over s e to the minus st. Okay, so I just copied this from above. So now let's see, I'm going to have an alpha over s times this integral. And I thought of this again as a function times the derivative of another function. So I'll keep my alpha over s times, and let's see, so I have uv is going to give me a minus cos alpha t, or cosine alpha t over s e to the minus st. So that's the uv evaluated from 0 to infinity minus the integral from 0 to infinity of v du. So v is minus 1 over s e to the minus st. And let me see, du, I get a minus alpha sine alpha t dt. So minus alpha, and I guess I'm kind of running out of space here, times the sine of alpha t dt. Okay, and this bracket closes off this bracket. So let's give ourselves some space. Let's come over here and we'll write alpha over s. And let's figure this out. So At infinity, this exponential function still is going to drive this cosine to 0. Again, the cosine just oscillates. But at 0, I don't have a sine to bring this guy to 0. So I have, again, at infinity, 0 minus, when I evaluate the lower limit. But now I have a minus cosine alpha t, so that's going to become a plus. A cosine of 0 over s, well, the cosine of 0 is 1 over s, and e to the 0, of course, is 1. So here I have a minus, and a minus. That gives me another minus. And let's see, I can pull out these constants alpha and s again. So I'll get alpha over s times the integral from 0 to infinity of e to the minus st sine alpha t dt. And if I distribute the alpha over s, let's see, I should get an alpha over s squared when I multiply times the 1 over s minus alpha squared over s squared. And at this point, we should be able to recognize that this is just what we originally asked for. It's just the Laplace transform of the sine of alpha t. So I guess I'll just write this as the Laplace transform of the sine of alpha t. And so now, let me just, I'll transpose, or I'll bring this entire term to the left-hand side. So remember, we still have this Laplace transform of the sine of alpha t just sitting on the left-hand side. I have a plus alpha squared over s squared times the Laplace transform of the sine of alpha t. And all of that should equal to, the only thing that's going to be left over is the alpha over s squared. So on the left-hand side, I'll just put it over here. I can factor out the Laplace transform of the sine of alpha t, and I'll be left with 1 plus alpha squared over s squared. And of course, to get the Laplace transform of the sine of alpha t by itself, I'll just divide both sides by 1 plus alpha squared over s squared. So I'll get alpha over s squared divided by 1 plus alpha squared over s squared. So I have a complex fraction. Let's go ahead and see if we can simplify this guy. Down here, I'll change the 1 to s squared over s squared. So I'll get alpha over s squared over s squared plus alpha squared over s squared. And so this becomes alpha over s squared divided by s squared plus alpha squared all over s squared. And if I invert multiply, I'll get alpha over s squared times s squared over s squared plus alpha squared, leaving me with the Laplace transform of the sine of alpha t, which is alpha over s squared plus alpha squared.